Hey, welcome back to another Statics with Python course. In this problem, we are going to deal with 3D forces and trying to find the resultant of a bunch of forces in the three-dimensional space. And so in this problem, we're going to write a Python script, a Python code, to solve for the resultant force of all of these forces acting on this little particle in the three-dimensional space. And as a quick note, I am going to split these statics with Python into 3 separate parts instead of just 2. I noticed that in previous videos when I tried to cram in the problem statement as well as the algorithm into one video, it was starting to get really crammed and very long. So hopefully breaking up these videos, these problems into 3 parts, where the first part is going to be the problem statement and just all of the statics that you need to know. The second is the algorithm, so developing the algorithm. And then finally, the third part is the actual coding implementation and writing the script in code in Python to solve this problem. So with that being said, in this problem, the problem statement says you have n number of forces acting on this little point A right here, and we want to write a script that can calculate the resultant of all of these forces, knowing, and this is important, knowing that the action, the line of action for each one of these forces goes through a point A. So what that means is that the line of action for all of these forces right here in red, their lines of action all intersect at this common point A. Now you can also see that I've drawn the line of action for each one of these forces in yellow, and I have a random point along that line written as point A. So for an example, this is force 1. A point along the line of action for that force 1 is A1, and it has coordinates x1, y1, and z1. And we have all these different points, A1, A2, AI, all the way up to AN, and each one has 3 different coordinates, right? X, Y, and Z. Now, the line of action for all of these forces goes through a common point, A0, and that A0 point has the X0, Y0, and Z0 coordinates. So, our first step in this problem is to really understand the problem. And that's what I've written here, understand the problem. So we already know that the coordinates are 2 points along the line of action. So we know that for each force, we are going to have 2 different points along that line of action to understand its orientation within this Cartesian coordinate space, right? So if we were looking at this force right here, we would need to know where the line of action sort of starts and then another point along that line of action, in this case A2. So we have 2 different points along that line of action, which goes right there. We have this A0 as well as this A2. And from those 2 coordinates, remember these are 3D coordinates, from those 2 coordinates, we can figure out the orientation of this line of action. That's going to be important because, well, we need to know in which way this force is acting, right, in 3D space. So we know that the coordinates are going to be 2 points along that line of action. Now, we also know that every single force shares point A0. So you can see that all these forces are being exerted onto this particle right here at A0. That's also going to be very important. And in order to find the resultant force of all of these different forces, we need to sum the components of each one of those forces, just like we did in the 2-dimensional space, where you take all the sum, or you take the sum of all the forces in the x direction, that gives you the x component of the resultant force, and then you sum all the forces in the y direction, and that gives you the y component of the resultant force. We need to do the same thing here, except in this case, we're dealing with 3-dimensional forces, so each one of those forces is going to have 3 different components, right? One along the x, the y, and the z axes. So in our problem, we're going to have to sum all of those components, and that's how we get the components of the resultant force. So once we have that, we know that we can represent 3D forces using this equation. And hopefully this equation right here is not unfamiliar, right? Whenever you have a force in 3-dimensional space, we can represent it by its value right here, F, multiplied by this lambda unit vector. And so the quantity f, the value, that's the scalar quantity of the force vector f. And this lambda unit vector, well, that's just the unit vector that represents the orientation of that force, right? So if we can figure out the orientation of that force's line of action, we know the orientation of the force. And that's obviously going to be really important. So let's look at this lambda unit vector. And hopefully, again, that's not something that's unfamiliar. If you've already done 3D problems in statics, you know that the lambda unit vector can be represented by this equation, where the x component of the lambda unit vector is this dx value, the y component is this dy value, and the z component is this dz value. And you can see that each one of these components is represented by an internal unit vector, I, j, k, which represents the x, the y, and the z axes or directions respectively. So you can take all these components and divide it by d. Now, what are these d values? Well, this d right here, that is going to be the distance between any 2 points that we're looking at. So for an example, if we're looking at this force right here, it goes from A naught all the way up to A2. And so the d distance is going to be the distance from A naught all the way up to that second coordinate, A2. And then if we look at the other components, dx, dy, and dz, the dx value is really just going to be the x-coordinate of the ending point minus the x-coordinate of the beginning point. So in this example, up here with this force, we're going to take x2 minus x naught, and that's going to give us dx. And then for dy and dz, again, you take the ending point here, y2 minus the starting y naught, and that gives you dy. And then the same thing for z2 and z naught, the difference gives you dz. Now, once you have dx, dy, and dz, we can figure out what this distance or this d in this denominator is by simply taking the root sum square of dx, dy, and dz. So you square all the components, dx, dy, and dz, you add them together, and then you take the square root of that value, and that's how you figure out d. Okay, so once we figured out all 4 of these components, that gives us this lambda unit vector. So we now know the orientation in which that line of action for that particular force is, well, oriented in. So once we have that information, we can determine the components of the resultant force pretty easily, right? If our resultant force, if we expand that out, we know it has a x component, a y component, and a z component. And we're just summing all the forces in the x, the y, and the z directions to get the rx, ry, and rz components. And that's pretty much it, right? This is just taking all the stuff that we've learned in finding the resultant force in 2D space into 3-dimensional space. We just have an extra component, rz, here. So once we've figured out all the 3 components of this resultant force, then we can use those components to figure out the direction thetas, right? And we need to figure out which way this resultant force is oriented in, and we can do that with direction thetas and direction cosines. So that's about it for the problem. Hopefully this is not unfamiliar. Again, we are just looking at a n number of forces for this problem, starting from A1 going all the way to AN. And the idea here is to look at each force individually, figure out what its x, y, and z components are, and then add that to the resultant's respective components, rx, ry, and rz. And once we figure that out, then we can find the orientation of that resultant force. So that is the problem statement. In the next part, in the next video, we are going to look at the algorithm, developing the algorithm to solve this problem. So it's not the code, but it's just the algorithm, all the steps that we're going to take in code to eventually write the script in part 3. So I will see you guys in the next part.